Hi, welcome to another video. So today, March the 15th, 2015, Sunday. So using the ESP8266 Wi-Fi, I'll show you how I pick up the temperature, forecast, time and date, and send this solar panel wattage up to ThingSpeak. What I'll do, I'll let this run through a couple of routines and then I'll show you the code. So the current temperature, 7 degrees C. Now I know that's a copyright symbol, but I prefer that to the normal degrees C symbol. It's obviously cloudy at the moment. It keeps on changing from cloudy to partly cloudy, so the wattage down here is low. That's now picking up the temperature. So at the moment I've got all these routines going on within a 10-minute time scale, just for demonstration purposes, but I obviously don't need the temperature every sort of 5 or 10 minutes, half an hour or an hour, depending on how often the internet site is updated, and same as the forecast, every half hour or so would be good enough. And the date, I only need that once a day. It's currently picking up the day and date every 10 minutes. So at 53 minutes it's now going to send that solar panel wattage. So connecting to BT, connecting to ThingSpeak, and data sent. And remember that wattage was about 3 point something. So for those of you who are new to my video, this solar panel current, voltage and wattage, that's the voltage on my batteries upstairs. And I've got a clock upstairs transmitting the solar panel current and wattage. Pick it up down here. It's a 50-watt panel in a west facing garden, so I don't get full power until the afternoon when the sun comes around. This data is transmitted via Bluetooth UART every minute. I've also got a video on my channel. I'll just capture this to an EEPROM and use it as a data logger and print a graph, but now with this Wi-Fi module I'm uploading this data to the internet. I'll show you how to do that. So I'll show you how to pick up the data and send some data. So while I'm waiting for the next update, I've got the Microelectronica's EasyPick Fusion version 7. It's a PIC32 MX795 microcontroller, and up there is the ESP8266 Wi-Fi module. So that's connecting again. I'll show you the routine. So that's just got the forecast, and you might see we've got a send OK. Sometimes I don't get the response send OK, so I've got counters which will time out and just give us the string down the bottom. So it's cloudy at the moment. When I first started this morning, it was partly cloudy and we had something like 8 or 9 watts. In the summer we get about 27-30 watts off a 50-watt solar panel. So that's just sent the solar panel data. Right, before I forget, this is the ESP8266 Wi-Fi module I'm using today. These are the connections. 0 volts over here, power over here. To use the device and enable the chip, you put power here. On my board today I've got this wired to a port. When I finish using the device I pull this down to ground. When I want to use the device I turn the port on. These are 3.3 volts only. If you've got a 5 volt microcontroller, have a look on YouTube, find some videos on level conversion. Anyway, this is the RX pin, goes to the TX pin on your microcontroller or the TX pin on your TTL to USB adapter, in case you want to try it on the internet first, which I highly recommend you do. Try it on the internet. You need to know what sort of data is coming back from this when you send various commands. If you hadn't seen my previous video on the basics of this, you should really have a look. This is a TX pin over here. This reset isn't used, so it's disconnected, and this GPIO 0, if you need to flash the device, pull this down to ground and update the firmware. Right, in case you're not familiar, this is thingspeak.com, and what this ThingSpeak does is allow you to capture data from the internet, data from a web page, and pass just a small string. Pass meaning compute. So this web page, for example, is predominantly a picture, but many web pages, whether you're on Facebook or MSN, Google, whatever, it will have lots and lots of data scattered everywhere, lots of pictures, and the data will probably amount to many thousands of bytes or hundreds of thousands of bytes. And what this does is allow you to put in a web page, URL, unique resource locator, put in a web page, capture just one bit of data, just the significant part you need. So create yourself an account, it's free to use. I'll start with the basics, go to apps, so apps for applications, so this thing HTTP, and you can see I've created 4 already. So temperature in Barnsley, yes I'm in South Yorkshire but I'm not a Barnsley man, I'm from Surrey. So look, I've got the forecast, date, time and temperature, and that's what you saw on my TFT. So let's go for forecast. So this web address here, that's the URL, unique resource locator. You put in the URL of the web page you want the data from, and then down the bottom it says pass, look, compute, pass string, and this is just the small bit of data from that massive web page. Well, I've previously captured this weather using video capture, and I noticed there was a big advert, and I don't want to get done by YouTube for having paid ads in my video. So now I've actually picked up a different site, but using this Google weather forecast as an example, say I want that temperature, right click in Google Chrome, inspect element, wait for the element to come up, pull this element over. On the right hand side here is that path to that 9 degrees, so if I move up and down you can see the various strings for various bits of data on this web page. Now on the right hand side you will see there's thousands of bits of data, or thousands of bytes of data, including pictures. Now a microcontroller would struggle to pass all of that. I only want this one bit of data. So on this highlighted part, right click, copy XPath, go back to ThingSpeak. So this is the URL for the weather, and then from the XPath you copy and paste the XPath down here. So if I go edit, for example, I won't change it because my microcontroller is using it. I would paste the XPath in here, and obviously paste the URL here. And then the method to get this data, you type in the word get, well, it's already there by default. You use the word get on your microcontroller. The HTTP version is by default is 1, so you can just leave it at 1. Although currently I don't know many internet sites that use 1, they will use 1.1. And then you save your thing down there. So save thing HTTP. So I'll save it. Now on the right hand side here, if you right click, copy, this is giving you a URL to go and get that passed data here. So look, HTTP, API ThingSpeak, and then a read code at the bottom, which is an API key. ThingSpeak give you an API key to read various bits of data you're asking for. So you copy this URL over here, copy, open a browser, and there we go, it sends back cloudy. It'd be nice to have just 5 or 6 bytes of information to pass on your microcontroller, but unfortunately when you request this bit of data you get a string of maybe 500, 600, 700 bytes long. I'll show you an example. So from that web page I've now got cloudy, and all the other pictures, all the other data is ignored. So back to thingspeak.com. Here are my HTTP things. Now you can set up as many as you like. I don't think there are limits, but if I click on this temperature in Barnsley for example, every time you create an HTTP thing or thing HTTP, you do the same. Put your URL here, pass the string here, but for every individual thing HTTP you get a unique API key, and that API key is the only thing that changes. So in your microcontroller, when requesting data, you put in this string, key equals, and then just change the various API keys for the different requests, and that's all I've done on my microcontroller. So that's thing HTTP. Then there are channels up here. So my channels, there are public channels, watch channels, I haven't watched any, but they're public channels where people post data on their channel and you can go and view it. So if I give you an example, my channel, you can make them public or private. So there's my channel here. So from just before 10 o'clock this morning, it's about 9:30, I've been sending my solar panel wattage. So if I hover here for example, you can see 12:38, I had 74 watts. Now because it's a cloudy day, I've actually multiplied the watts by 10, so that equates to 7.4 watts off a 50 watt panel. You see it got more cloudy here, I had 0 wattage, and up here 178, so divide by 10, 17.8 watts, and you can see the cloud has been coming and going all day. So that is my solar panel wattage that I've been sending up to this free channel. So the last time it sent the data, 14:53, I had 18 watts, so that equates to 1.8 watts. Just before we see the code, what I forgot to mention, so on this public view channel, there's my data coming in. So this is sending data, not requesting. So I'll give you a quick demo. So channel settings. So ThingSpeak give you these fields here. So for this solar panel watts, I'm writing to this field, and you can type your own definition here, and that's what you see on the chart. So I typed in solar panel watts, And look, so we're now at 1528. My forecast is mostly cloudy, and I've got 8 watts, or another bit of data has just come in. 1528, 8 watts. That equates to 0.8 of a watt from a 50 watt panel. So that's channel settings, API keys. So when you're requesting the data, you look at the key on your apps. So you look at these various keys over here. So that's the URL. Type it in there, as I said before, and you can use the internet to access this data, or your microcontroller. So back to channels. See this API keys here. So this is the right key, and for your channel this key is going to be unique to you, and to write to your chart, to send data up, use this right key. So data import export. So you see here they give you a URL here, and you can still use the word get even though you're posting data. You still put get here followed by this field here and the field you're writing to. So in my case it's field 1, and if you see the AND symbol there, that's the data for that field. So in this example, that 0, you'd be writing a 0 to that field, but that 0 in my case is replaced by solar panel wattage, and I'll show you this in the code. So that's to post the data, and that's to view the data. So I'm using the internal RTCC, and with those colons flashing every half a second, I'm synchronizing my program. So I've just noticed here, so this is when I was running the camera, so a lot of these functions aren't used, so just ignore them. If I don't mention them, it means they're not relevant. But so this is the half-second bit from the RTCC. Now if you're not running a clock, you'll have to put delays in a routine or use interrupts. But because I'm running a clock, you can see when I've got the half-second bit, I flash the colon in white. This is important. This clears the overrun buffer if you get overrun buffer errors or frame errors in the UART. And before I forget, I'm using 9600 baud rate. This is the second half-second bit. And I've got the once so that this routine only occurs once. So you can see here, I was flashing the colon white, and now I'm flashing it black. So this is where this time comes from the internal RTCC. Now every time it flashes black, so in this routine, I've got all these routines here, so look, 0, 2, 4, 6 and 9, so they're all OR. If the routine equals 0, or 2, or 4, or 6, or 9, start the Wi-Fi counter, then I've got a get data counter. I need this because if you don't get a send OK, you have to end the routine at some point. So this is like a timeout. And then this fail counter is if I don't get a reset and ready signal from the ESP8266. So that's what that is. If the get data counter got to 60, it means something's gone wrong because it shouldn't ever reach 60, and I'll show you in the code. It resets the get data counter to 17 and resets the Wi-Fi counter to 17 because the programs start doing something at 20. So that's what this is. So that's my timing here, and that's all my routines are based on this Wi-Fi counter and get data counter and these routines here. Now in this example today, I've got buffer sizes here 760. I had a counter on the screen and they went up to about 720 at one point, so I've put them at maximum size 760. Then we've got 2 temporary buffers here, These will make sense when you see the code. This clears the buffer when we're done with it. This saves the message. So unsigned int I. But for I equals 0, I is less than max message received, I++. Then there's the temporary buffer, I, new received message, I. So it's creating the new message from the temporary buffer. So I've got this bit ready, doesn't apply to this program. So unsigned char, new byte. This is the string, so I can put it on the TFT. This line and X is, I was displaying the bytes on the TFT. Message terminator, so 10, up to your ASCII chart. A 10 is a line feed, ASCII 10. So when the message ends with a 10, you know you've got a line feed, which is the end of the message. So I've got char, new message available, RX2 counter, the string because I was putting it on a TFT, a state you'll understand later in the program, unsigned short state, 0 them to start. Then this is the UART5 interrupt, so it's high level, ICS auto, static unsigned int RX counter equals 0. Then this is when the data comes in. You get the UART5 interrupt flag bit. New byte is UART5 read. If the new byte is equal to the message terminator, which means it's the end of the message, clear the temporary buffer and reset the counter. If new message available is equal to 0, it means it's been read further down in the program. So then at the end of that bracket, clear the new message, temporary RX buffer, RX counter equals 10, so putting a null character at the end of the message, new message available equals 1. So you can then read the message. Else, if the RX counter is less than a max message size, which is 750, temporary buffer, and then the counter equals a new byte. So every new byte, the RX counter starts incrementing. You can see there, RX counter plus plus. Now, so that I can use the counter elsewhere in the program, I've got RX2 counter equals RX counter, and then save new message. And this save new message is up here, save new message. And that's it. So a small break before we clear the interrupt flag. So you can see I've got a note here. This function inspired by Dave Fisher at Rose-Hulman Institute of Technology. I saw his channel and he had this clever function of passing a string of varying length. I've modified it a small bit. Let's put this state up here, for example, and only saving the message here, not here. Well, this is how I'm grabbing the string. So now you've seen how I grab the data. Ordinarily that program would read this line and put a null character here, but I want this data, all of this. I want this line and that line. I can't search for every individual Saturday, Sunday, Monday or whatever, or cloudy, mostly cloudy. I want this X request here. So it would be okay to put a null character here and delete all this, but it's easier to just let all the data come through. I'll grab this and then it can clear the buffer. Right, so in my program I've got a couple of routines. One is to go and get the time from the RTC, then the other routine Then the other routine is to show the time. And then in the show time routine, which only lasts for half a second, I go and get the forecast, get the temperature, get the time, day and date, that sort of stuff. So here's the primary chars and ints I use for that. So you can see there's routine there, got temp, got time, got temp, got date, got forecast, send data. And the program starts with routine 0 when I first turn on, go and get the time. Then you've got a bit for the Wi-Fi reset, constant char OK equals 1, so that never changes. Then that's a char for the OK counter, string because I was putting it on the screen. If you see any strings and I don't mention them, it's because I put the data on the TFT. So the program is similar to a state machine. So I've got all these states and they'll become apparent later on. Then I've got these temperatures, then the results, then you can see like year 1, year 2, year 3, year 4. That's all the different positions in the strings. Then Wi-Fi, then you can see the months. To pick up the months I had to look at 6 individual bits to work out all the permutations for 12 months. And when I started doing this I thought, well, maybe I'd stick to the Bluetooth, but so these are the 9 days of the week, Monday, Tuesday, Wednesday. Then the forecast, 14 different strings so far. I've seen cloudy, rain, rain late, mostly cloudy. So I'm looking at 14 different strings there, and by default they are ASCII 48. So ASCII 48 is a 0. This you'll understand later in the program. Strings available, and then I'm displaying on the screen. Results. Right, these searches, I've got various searches on here. They return a position of an ASCII character. So the string, as I said before, always starts with X-request ID. And so in this particular string, ASCII 79 looks for the O in OK. It's an ASCII character. I developed this ingenious method. I don't know, maybe other people have got it, don't know. But I thought, how could I find a character in a string? So I use this if and do loop. So because I know the string is at least 120 long, and I know the OK is going to appear up near 100, I start the string at 45, and look, if the string position is not equal to the O, ASCII 79, if that string position 45 is not equal to the O, do until that. So do string position plus plus, so increment from 45, 46, 47, 48, keep on going until, so while, until that string position equals 79. ASCII for 79 for OK. So it's incrementing the string position. Once it finds the O in OK, it returns the result. So the result 2 in this case is the string position. Return result 2. And it will tell me where the O in OK is in that long string. So we've got all the strings, as I said, start with that. So this is looking for the ASCII character 62. So I know this is looking for that greater than symbol. If you've got microelectronica up to the ASCII chart, 62 is here. So ASCII character 62. This is looking for that ASCII character, increments the string position until it finds 62, and it returns the results 5. This is the day of the week, and it's looking for what character appears in what position. So you can see in the string on Sunday, for example, a capital S appears in position 6, ASCII 83, so that's weekday 0 for the RTCC. Because of the permutations for Tuesday, I've had to use day 5, and this is the get month, which I haven't finished yet. October, for example, we have a lowercase o in the 4th to last position, so 4th to last must be October, and I've done the same for the other months. These aren't used at the moment. That's switch case for the weekday and the year. This is writing the time. If the program isn't running through any of the routines, it displays the time. And then this, for various minutes and hours of the day, different pictures on the memory card come up on the TFT. And then during that 59-second period when it's displaying a picture, if the forecast is okay and the string available is less than 11, I display the first 6 parts. So that would be cloudy, for example. If the string available is greater than 11, I display 14 parts. So that would be, for example, mostly cloudy. So in those searches I created, I thought they were really clever. And then one day, a few days ago, my whole clock was hanging. I just had a blank screen, and that's because it couldn't find the OK. The data was corrupt. I think I hadn't allowed enough strings in the buffer. So if it couldn't find the OK, you need to do something. So while I'm passing the string for the date, I put an OK, or put the O at position 180, knowing in the normal string the O will appear before 180. So if it can't find the O but it finds an O at position 180, I've got the fail to find the OK in date. I zero the date so it finds it again. Routine 8 is just a nothing, doesn't do anything, and this is where I'm turning the Wi-Fi off. Right, I've got 3 routines in this program: get the time, show the time, and then a while one loop. So if I explain one of the simple routines, so because of the RTCC splits the minutes and seconds up, you can see I've got minutes 1s is equal to 2, 10s is equal to 2, and seconds 1s is equal to 5. So 2 minutes, 25 seconds. The zeros that got temperature, turn to Wi-Fi on. You can see if the minutes is equal to 2 and the seconds is equal to 30 and the got temp isn't equal to OK, reset the Wi-Fi. Routine equals 2 for get temperature. Zeros are states. Get data counter equals 30. OK counter equals 3. Wi-Fi counter equals 17. Now I've started here because when I first turn on, the time brings the OK counter up to 30, and the get data counter starts, and the get data counter ends near 30. So I don't want to interrupt or interfere with the time routine, but otherwise all my other functions run like this. So that's the temperature, that's the date. Because I'm generally only getting the date once, I turn the Wi-Fi on here and reset the Wi-Fi because it's not being zeroed here, because as I say, I'm only getting it once. Once I've got it, no need to go and get the date again. The forecast at the moment for this demo, I was getting it every 6 minutes, so 6 minutes and 25 seconds Wi-Fi turns on and 0 is the forecast. So 6:30 I get the forecast if the forecast isn't okay, which it won't be because it's just been zeroed there. Reset all the states, get data counter, OK counter. This routine is sending the data, so I don't have to say if the data is not sent, because I'm just sending it every 3 and 9 minutes. So this is the while one. So when we are in a routine, the Wi-Fi is turned on. So if RB8_bit equals 1, that means do this. So I'll get a little window top of the screen. I'll show you again in a minute. We can see what the counters are doing. And then when the Wi-Fi is turned off, we get the seconds in the little box at the top of the screen. So again, when running a routine, we turn on the counters. So we start at the beginning. So if the Wi-Fi counter equals 20 and the reset Wi-Fi equals 1 and the state is not equal to OK, we send an AT and we're looking for the ready. When we get that ready, it means the state is OK. So if the Wi-Fi counter equals 20 and the state is OK, we set above state, and state 2 is not OK, we send the AT plus CW mode equals 1, and that responds with no change. So that state 2 is satisfied. Then we send the AT SIPMUX equals 1, which you've got to do to join a network, and it responds with SIPMUX. So that gives us state 3. This, we don't need to list the access points. I already know what my password and everything is, so you can list the access points if you want, which would be AT plus CWLAP, but we are just going to join the access point, and that's my particular home hub, and that's my password. Come and sit outside the house, put those bits of data in, and you can have some free internet, but you'd have to sit outside the house. Because there's a comma here, the compiler would actually split up the routines and not send it as one statement, so we do it this way. And then character return, line feed, and I've just got a message connecting to BT, and wait 7 or 8 seconds, and state 4 is OK. Now I could join the router, join the home hub, and then go and check to see what network I'm joined to, but I don't bother. I just state 4 OK, and that never fails. So again, because of commas, I've had to split this up. So SIP start, TCP, API_ThingSpeak.com, port 80, you've got the commas, quotation marks, and then connecting to ThingSpeak. And that's, we get a reply via the Wi-Fi of linked, so that gives us state 5 OK. Then routine is not equal to 9, which means we're not sending data, and the Wi-Fi counter is equal to 20, state 6 is OK, and state 7 is not. This is state 7. AT plus SIP send, 96 bytes of data, remember count your string, and then we just write that on the display. So this responds with that greater than or angle bracket, so we're looking for that in the reply, and that means state 7 is OK. Once we've got that, API ThingSpeak is then waiting for this: get space https API_ThingSpeak.com apps thing http, remember we got the key, That's the individual key for the time. So we're sending that space before the HTTP, character return, new line, character return, new line. That's another way of writing it in the compiler instead of 10 or 13. And here we are writing state 8 is OK in case we don't get a send OK. So when this state 8 is OK, we're then telling the interrupt, don't clear the buffer after every line. We want all the data to come through. So apart from this state satisfies this, we're then telling the interrupt, don't put a new line character after each line. We want all the data to come through. If I jump to one of the routines, now I've changed the numbers in this routine because I'll show you on the display in a minute. So if the routine is equal to 0, means we're getting the time, and the get data counter is equal to 35. This would normally be 10, but I've raised it to give you a quick demonstration. If we don't get the send OK, by the time the data counter gets to 35, we're going to say that routine is now equal to routine 1. So it's like timeout. If the routine is equal to 0 and the state 9 is OK, it means we did get a send OK, and we could jump immediately to the routine, to routine 1. Now this sort of happens for 8 seconds if everything's OK. Otherwise this is going to be something like 15-20 seconds. So if routine equals 1, got time is not OK, just change this figure. So if the routine is equal to 1 and the got time is not OK, we set the get data counter to 36 so that this isn't done anymore. We zero the state so that this isn't done anymore. I'm putting the line position on the TFT at line 5, clearing the screen. This is displaying the bits on the TFT. This is searching for that string here. So str is looking for the first instance of this ID, x-request ID. So if that string is OK, search string 2, and that's where I told you we're looking for the OK in this string, looking for the O in the OK. 2 millisecond delay. I found the delay does make the program more reliable. So I'm printing the string at the bottom of the screen. So search string. So if the string 63 is equal to 77, that means we found a P is located here, so it's PM, and then you can see the Wi-Fi hours is equal to the string position 53, Wi-Fi 10 hours, then hours 54, there's colon, Wi-Fi 10 minutes, minutes, seconds, seconds, and then AM or PM is here. And unfortunately they use a 12-hour clock on the internet, not 24. So if that position is not equal to a P, everything shifts up 1. So if we go back, so Wi-Fi hours is position 54 when it's PM. When it's not, it shifts up 1 closer to the OK, and Wi-Fi hours becomes 55. And this was just, this is one of the more simple routines. You want to have a look at the date where the month and day of the week, Monday, Tuesday, Wednesday, everything shifts up by many places. So you can see, so this is that string is not equal to a PM. That would equal to an AM. The Wi-Fi hours, seconds and everything are found here. Then I put a 2-second delay just now so I can demonstrate the thing on the screen. I've slowed everything down. Turn the Wi-Fi off. Got time equals 1. So I'll run through this second routine quickly. So this routine 2, looking for the temperature. If the OK counter is greater than or equal to 6 and the get counter is 43, means something should have happened by then, so it's timed out. And I'm changing from routine 2 becomes routine 3. And here, similar to above, if routine 2 and state 9 is OK, means we got a send OK, we jump immediately to the routine. So if routine 3 and got temp is not OK, it puts the get data counter 46, so a few above here, so it doesn't do this again. Clears state 9, so it doesn't do this again. That's the string, same as before. If the string is OK, this is here, we are putting a 79, so if you remember tools, ASCII chart, 79 is the O in OK. I'm putting the O in position 150, knowing that when everything is OK, the O is going to happen before 150. It's going to happen somewhere like 70, 80, 90. So if it gets to 150, something's wrong. This is just filling the screen, setting the font. That's displaying the data again. So this is at search string, goes off to search for the string, comes back with a position, with a result. So if the result is 58, there's temperature 1 and 2 are here. So temperature 1 multiplied by 10 to move it left one place, and then temperature 1. So look here, and then see here the result is in position 57, not 58. So it's moved left 1, so we've got less data, so now the temperature is single figures. I want to wait till the temperature here is like -2 or -3, and then that will screw up this routine. Then I clear the screen, 2 millisecond delay, turn off the Wi-Fi, got temp is OK. So this is the new message being received from the Wi-Fi via the interrupt above. So if new message available equals 0, so then the buffer can be cleared. And I've just reduced this now. This was previously set to 19, so every time a message comes in, the Wi-Fi counter jumps up to 19 and everything starts happening quickly, but I've reduced this to 17 to show you a slower demo. So in this string we're looking for the first instance of no change, and then we get state 2 is OK, and OK here gives us state 0 is OK, and we start counting the amount of times we've got an OK, because you remember from the routines some of the responses are just OK. If we've got ready, that means the Wi-Fi reset was OK, and reset Wi-Fi is equal to 1. If we get an error, routine 8 is just to do nothing. So 80 plus sitmux responds with 80 sitmux, that gives us our state 3. This is our link, so we say linked, that gives us our state 5. This is already connected when it does the routine again, so that gives us state 5 and state 6. That will satisfy state 5 and 6. This is the important character, this greater than or angle bracket, that means it's OK to send your request, so state 7 is OK. This is an abbreviated of send OK, you don't have to put the whole string in. If send is OK, state 9 is OK, and that's when the routine can jump immediately to the routine, to passing the data. And you can see connecting HTTP thing. At the end it's unlink, and in AT CW quit access point because I'm then turning the Wi-Fi off. And this is str searching for this x-request ID. That's the string we're looking for. So this is routine 4 to get the date. So I just want to reiterate about that search string. So here I'm putting the O in OK in position 180. So if it's running through the search and it can't find it, it would run all day, it would sit there all day. So, but because I've put it at position 180, it will find the O at position 180. During the normal routine, the O will happen sooner. So that's getting data. So for my sending the data, this is the routine. So 0, all the states again. Get counter, OK counter, Wi-Fi counter, the same. I don't have to ask, is the data sent not OK or whatever, because it's going to run through this routine, send it. If it fails to send, oh well, but it's not been failing for me. If I run down to the routine, show you how to send the data. So you run through the same, exactly the same routine if your Wi-Fi is starting at 0. So you test your Wi-Fi, wait for a ready, CW mode, no change, SIPMUX replies with SIPMUX, join your router network, SIP start, API ThingSpeak, and I think I said already, these have to be split up because there are commas here and here between this and this, and your compiler would split up the routine and it wouldn't work. Doing this routine sends it as one line, one string. So we're connecting to ThingSpeak on port 80 still, and then the only difference, so look, if the routine equals 9 and the Wi-Fi counter equals 20, state 6 is OK and state 7 is not OK, which is this state, AT plus SIP send, and then your bytes. Now your bytes has changed because the data you're sending is a lot shorter, so count your string. In my case, sending 2 bytes of data plus a carriage return and line feed, I've got 73 bytes. This is routine 9 to send data. So the get with a space, HTTPS, so that's HTTP secure, API ThingSpeak.com, update key, and that's the right key, and then the AND, which is the AND for the field. You can see field 1 equals my solar panel wattage string. You have to convert your data to a string, so look, byte to string, watts data string. And then today, in case I haven't said, because there's been no sunshine, watts data equals watts, and I'm multiplying the watts by 10. So that is how you send data. Obviously you'll have your unique key here, but you copy this off the screen, put your key in here, and you're away. This took me a short while on the terminal with a Wi-Fi module, the terminal on the PC connecting to ThingSpeak before I got it to work, and this routine's spot on. So that's to send data. And just the one above, you can see forecast request. That's to get the data. That's the date, and the only thing that's changing is this key here. So depending on what microcontroller you're using, you should find this works fine. And you can see there the primary difference between the SIP send is how many bytes For all the routines, it's 96 bytes, whether you're asking for the temperature, wind direction, weather forecast, day, date, time. But sending the data, you can see the string's a lot shorter. Just count through your string, including the carriage return and line feed twice, and then put the result there if it's different to mine. Hopefully this has helped. I'll just give you a final quick demo on the screen. I've slowed everything down to show you this routine. So as I say, for humans waiting for the microcontroller to do something, I had to slow everything down. So I started with a Wi-Fi counter of 20, so that was effectively giving me 10 seconds before something was going to happen. So 10 seconds this would happen, then and I zero the counter, then another 10 seconds this would happen, and then as I became more familiar and things were working, I figured if I get a response from the Wi-Fi module, let the Wi-Fi module set the counter to just below this figure. So in the routine you first saw when I first started this morning, if I get a response from the Wi-Fi counter was defaulting to 19, so I had half a second before it became 20. So now I've put a long delay in there, and I'll show you again, and I'll pass 500-600 bits of data on the screen, and you can look at the speed. Right, I'll reset this microcontroller and you can see everything happening slowly. Hopefully you can see the OK counter on the left and the Wi-Fi counter on the right and the get counters in the middle. Hopefully this will fail to get this send OK. So you can see the counter up here counting. Every time the data comes in, I'm starting from 17 instead of 19, so it's all happening slower. Oh look, right, so we haven't got the send OK. Now I've increased this get data counter to 35, I think, so it's going to time out then. We didn't get the send OK, and that's passing the data coming in. This is about 550 bytes just for the time down the bottom. And you can see it's now going to update the clock. We're on 5 seconds here, so you'll have to wait a minute. And this is running at the normal speed. So it's 8-second delay for connecting to the router. I've still got this long delay. I should have cut this delay down. This data would be ready in sort of 10 seconds, not 35, which this is going to count up to. You see, this is the solar panel data come in just now, so 7:30 at night, and we had very little current. So that's the data, that's the string at the bottom. And in 1925. So just go through the routine, get the date, get the temperature, get the forecast, send the data from the solar panel, and that's it. So if you want to know more about 7-inch or 5-inch TFTs, have a look at my other videos, including the touchscreen. That's the PIC32 MX795 microcontroller, but this routine using the Wi-Fi, you could probably get away with little PIC 16F84A, or maybe something a bit bigger, something like 16F877 or 887, something with a UART terminal. UART terminal running at 9600 baud rate. It doesn't have to be a 32-bit at all, just a simple 8-bit microcontroller. Maybe you're running Arduinos and you don't know the code. Hopefully this video will have helped. Actually, we're on 6 minutes and it's just kicked in, so this is going to pick up the forecast. So let's watch it get the forecast. And I haven't increased any of the delays, so this all should be quite quick. And we didn't get the send OK, so this is going to time out at 45. And there's the forecast down the bottom. Weather phrase runs off the screen because the string is so long. And there's our forecast at the top. Mostly cloudy still. What a miserable day here in the UK. So while I've been doing this program, we've got many more bits of data sent here. You can see ThingSpeak compresses the graph, but that was our peak, sort of 2 o'clock. We got a moment of sunshine. That's over sort of 5 or 7 minute period. So within 10 minutes we had a burst of sunshine, and then we've got nothing. This is where it's been unplugged, where I've been running through the program. These are all nothing, nothing, nothing. If I hover over it, see 0 watts, 1 watt. Remembering I'm multiplying by 10, so that 1 watt there at, I don't know, 5 o'clock, something like that. I don't know, 1543. 1 watt is actually 0.1 watt. That's what a dull day we've had. And I've just turned it back on. Here we've got no watts, 0 watts, so we're less than 0.1 of a watt. But it is pitch black outside now.